Hello everyone, my name is Jose, I work at Dott and we're here to discuss distributed transactions. So why this topic? Basically, because it was a hard lesson for me. When I first heard about microservices, I got really excited. I tried to learn new frameworks, I tried to read more about domain-driven design, how we could build our microservices well-defined, with clear scope. And I pitched this idea to my company. We start working on some services, but something was not quite right. And then it hit us. For the first time, we had to distribute data across several services and the same transaction. And then we got familiar with this quote, because we had two choices. Either we ignore the problem and hope for the best, or we implemented a solid solution to handle this issue. So when I talk about distributed transactions, what's really the issue here? Let's take an example from our marketplace at Dott. Let's say that a buyer wants to purchase an order. It's a simple scenario, right? Well, not quite, because you have this layer of services and dependencies. You have a catalog service to make your products available to the buyer. You have a stock service that will handle inventory. And then once the purchase is made, you need to manage seller interaction. You need to make user registration. You have to have a message service to handle all the communication between these two entities. And also logistics and operation. You need to handle payments, you need to manage package tracking, deliver the package to the buyer, and then you have the invoices. So what's really the problem? Well, what happens when we submit the order and then the payment fails? What should we do? How can we make sure that our data is consistent? So should we delete the order? Should we retry the payment? What's our strategy here? Oh, and by the way, some of these services are external services, so we are not fully in control of the solution that we are going to adopt. We need to take this into account when we are going to build this relation between services. So ACID properties are really compromised here, right? Because once you had a set of statements, but now you have service calls. And also, you are used, in a traditional database, you are used to have constraints in your database, but now they are distributed. Are you going to consolidate all these constraints? Isolation is also an issue because in the past, once you started a transaction, if a new one comes in, you wait for the first one and then you try the second one. Now you have concurrent service calls and you had to deal with network issues. Durability is also a problem because in the past, well, the serious problem that you had to manage was disk I/O. Make sure that you are going to persist the data in your database, but now you have to handle network issues. So this is the scenario. How are we going to solve this problem? Well, let's go back to basics. I don't know if you have ever had the chance to choose a database for your project. But if you did, you probably stumbled upon this theorem. The Cap Theorem says that you have to choose two out of these three features. For instance, if you choose a relational database like MySQL, you are going to choose consistency and availability, but it's harder to build partitions. If you go with a database like Couchbase, it's easier to build partitions, build nodes in your database. Your data is always available, but probably you must be ready for some lack of consistency. For instance, MongoDB follows a different approach. It's also easy to build partitions. Your database will always be consistent, but you probably will lack of data availability during that consistency. So why am I showing this theorem? Because I believe that this is also relevant when you are going to choose your solution to solve this problem of distributed transactions. Let's think about this. Well, when you build microservices, you are partitioning your system, so you already made a choice here. So now, in your solution, you have to choose Either you want consistency or either you want availability. So let's look at some solutions. The first solution is a two-phase commit protocol. This protocol has been here for a while. It has several specifications. One of the most well-known specifications is the XA specification, which has several implementations in many languages. But the principle is always the same. You have a state server, which is going to mediate a voting phase, where a prepare command will be sent to all services, and the services will change their data into a prepare state just before committing the data. Then all services will apply those changes, and then we are going to the ready. All the services will send a ready command to the state server, and then the first phase is completed. Then we'll go to a second phase, which all the services will persist their data. This protocol works very well for systems, for an application which has several databases. Doesn't work quite well in microservices because it leaves many decisions out in the open. For instance, what happens when we have network issues during the persist phase? What should we do then? So this takes us to the second solution, which is the Saiga pattern. The Saiga pattern tries to have a more complete solution. We have an orchestrator which is similar to the state server, but instead of having a voting phase, we have the list of transactions that we want to do. We provide a command to persist each transaction. If an error occurs, like in this case in the third transaction, we have a compensation process in which we have a rollback transaction for each one of the transactions that went successfully, and the system tries to go back to the initial state. We have more control here. We have a similar approach to ACID transactions, but we have an extra layer of complexity. This means that for each transaction that we're going to do, we'll have a rollback transaction, which leads to possible bugs. And if we have bugs in a rollback transaction, we may still have invalid data. So this also takes us to the next solution. So instead of trying to build an always consistent system, let's think about a system that will eventually be consistent. What does this mean is that instead of having an orchestrator, we are going to send events from transaction into transaction, and the system eventually reach a consistent state. In this case, we have the order service that creates the order, will provide an event to the stock service. The stock service will confirm the reservation, the payment will be created, and then goes back into the order service saying, okay, the order is completed. Here, it's a way simpler solution, but we have to be ready for the lack of control, because now we don't have the full control of the entire process. So what was our solution at Dott? First, we did some assumptions. We're going with optimistic transactions, which means that we do all the validations up front. All the validations are executed successfully, and now when we submit a transaction, it must be persisted. We must make sure that that transaction must happen. We also built stateless and independent checkpoints, which means that we are going to monitor the entire process of the distributed transaction into checkpoints where we confirm that the process is at that specific stage. And they don't know each other, which means this is why they're stateless, because they should work alone. The system should also be self-healing with automatic retries. So we can, if something goes wrong, the system should recover itself. So basically what we want is the control of Saiga on one hand and the simplicity of eventual consistency. So let's look at an example to understand the solution. This is also a real scenario here at Dott, where buyers purchase orders and we handle payments in the name of the seller. So periodically we need to pay the sellers for all the orders. this seems like a simple scenario, but actually it has several transactions here in this process. So first we need to reconcile all the orders. Then we need to process bank transfers, process our commissions, generate the invoice, and update the seller balance, and then notify the sellers. So each one of these transactions is done in the separate servers. Oh, and again, we're having external services here in the mix, so we need to handle the process taking this into account. So what we did was creating this entity that will understand what is happening at any given point in time of this transaction. We call it data omniscient transactional state, not for any valid reason other than the fact that we like to say that we use Dott at Dott. It's just a matter of speaking. So the first step in this document is to identify our checkpoints. So the document must be built with already all the checkpoints in place to monitor the process. And then the process starts. The process starts, a transaction ID is assigned to that process. We guarantee isolation because if a next request comes in, it is locked. We are already in progress with this transaction. And here we have another feature that we see. We have a field, we have a Boolean field here saying reconciliation status is valid. If it was invalid, we can abort the transaction and say, okay, this isn't a failed state. It requires manual intervention. And the process will stop and will not accept any upcoming requests. And so the process then goes on. It has context information to the transaction so we can make decisions. More information until the process ends. The document is marked as completed, the transaction is done, and then no additional work is required. So in broader terms, this is our solution. So where is the reactive approach? It was on the title of the topic, right? What do I mean what it means for the solution to be reactive? First, we need to think about what it is reactive programming, and this is the simplest solution that I found, the simplest definition that I found. You need to change your mind about how you think about your code. First, in the past, probably you look at your code as a set of statements, but with reactive programming, you need to see your code as a set of handlers that will react to something that happens in your project. There are a lot of reactive libraries out there. This is an example from the Reactive Library that we use, which is AkaStreams. The principle is basically the same in most approaches. So we have a source of information. It can be a database, a file, a queue that will feed information to a flow. A flow will transform the data and then will provide this data to a sink or a consumer, a destination. It can be a different database table. It can be a consumer that will handle the data and do something with it. I added also some nice features of this library. We have back pressure, which means that we pull from the source at the same pace that we can consume the data, so our system is not overwhelmed. And we have asynchronous boundaries that allows us to scale individually each process, each step of this process. So again, where is the reactive approach? Basically because each one of these steps is converted into a subscriber, an individual subscriber. And instead of having this chain of hard-coded dependencies between them, you will communicate through events. So each event, when a single subscriber finishes, it will send an event, it will acknowledge the message, and this event will be consumed by the next subscriber. They don't know each other, they only communicate through these events. So the reconciliation will send a payment ready event, the payment subscriber will mark the payment as completed and will send an invoice ready event, and so on. This uses a pub-sub publisher-subscriber approach, and also each one of these subscribers has a state machine. to have a full control of this process. So in this example, the reconciliation process of this transaction already finished. It was marked as completed. We have 3 pending checkpoints, the invoice, the seller, and the notification. And the payments we can have multiple status when a process is being executed. In this case, the payments can be in progress. It can fail and it's retrying, or it can fail all along and manual intervention is required. We have an alerting system in place. If a transaction is marked as failed, we require manual intervention to fix it. I cannot end this talk without showing some code, of course. We have here a reconciliation subscriber, which is an example, which is a code sample from the example I shown previously. In order for us to register a subscriber, we need to extend the stateful process, which gives us all the features that I've shown in the past. The only thing that you need to worry about is these 3 methods, in most cases. You have to assign a transaction ID to your subscriber. In this case, we are building a transaction ID based on the seller ID. You have to define a prepare new state, which is a method that states how this document is going to be built. And then you have the process method with all your business logic. So here we're using Scala. We have 3 stages in this subscriber. We are preparing the data, we are calculating all the balances, and once this ends, we are publishing the next event, and we are marking that the process has done. The global state is marked as pending because this is the way we have to release the lock on this process. So that's it. This is it. You define your subscriber. You assign an identifier so that subscriber is assigned to the whole process, the process that it belongs to. And then we have the next sample code. We have a finance service. This is a sample of our loader class where we register all our subscribers. In this case, we are instantiating the reconciliation subscriber, and we are also assigning a validator which allows us to define exactly the rules for us to accept that message and process it inside our subscriber. So this is it. This completes my presentation. Thank you.